Okay, good afternoon, everybody. As the gentleman mentioned, I'm Director of Engineering at Pilot Systems. We're a small business in Farmington Hills, Michigan. We focus primarily on systems engineering and controls development. We work across the defense and auto industries. At the back of the room is my colleague, Dr. Jordan McBain. He's the inventor of this really exciting technology that I'm going to talk about. This is potentially massive potential for operational improvements, efficiency improvements across Army platforms, including ground vehicles and VTOLs and drones, aircraft, pretty much the whole gamut there. So this is electromagnetically controlled pitch for blades, fans, propellers, turbines, basically anything that moves fluid. Okay, so the analogy we like to use is, imagine if you're driving down the highway in your car and you're stuck in first gear. So if you do not adjust the pitch of blades for propellers and turbines, etc., basically that's what you're doing. You're driving down a highway stuck in first gear. Now, pitch actuation and pitch control has existed for decades, but the incumbent technology is primarily hydraulically actuated. Sometimes it's pneumatic, sometimes it's manual. But the hydraulic systems, they're inefficient, they're heavy, they're expensive, they're maintenance intensive, and of course it's a non-starter for any platforms that do not have incumbent hydraulic systems. Hydraulic actuations used in large machinery, so I think mining applications and large aircraft applications. But as I said, for systems which do not have that, so think potentially eVTOLs, for example, it's just a non-starter. And really importantly for the warfighter, if you think about a silent watch situation, that demands optimized airflow with minimized power draw. So that's really what we're aiming for. So imagine if we could decrease power consumption for tactical and combat vehicles. Imagine if we could triple the operational range of drones. Imagine a simple way to reduce acoustic and thermal signatures, potentially a 2x silent watch capability, shorten the logistics tail by reducing the fuel burden. So those have kind of been our guiding principles in this. So on IFVs, typically the third largest power draw is cooling. Typically how this has been achieved is hydraulic control, as I said, and it's on-off actuation of hydraulic fans. Beyond this, obviously I mentioned potential benefits to VTOLs. And just to illustrate the power saving, so for agricultural applications, there have been studies performed that for every 2 degrees of pitch angle changed, which in agriculture is typically done manually, there's about an 8 to 10 amp drop in the current drawn. So this is really significant. So back to my first analogy, stuck in first gear. So there's a company called Allen Bradley, or ABB. They did a bunch of various studies into variable speed drives with an effort to improve fan efficiency. They concluded that running the fan at half of the speed actually uses about 1/8 of the energy. So you can see how significant this could be. And to increase the airflow, you simply adjust the pitch of the blades. So they've cited many examples. You can see some of them here, but for example, there was a power plant in the UK. They saved 1 million kilowatt hours over the course of a year, and the payback period for introducing variable speed was about 16 months. So there's links to these findings here. You'll see them in the white paper as well, if any of you guys are interested to refer to those. So right now, there's a market that is totally unmet in terms of needs for variable pitch control. And right now, it's focused on large equipment, large aircraft, etc. And then if you think about small applications which could benefit from this, small to medium VTOLs, it's really completely unmet because the swap-C equation does not make sense for those applications. Now, the benefits of our technology, which we call EMCP or vector mag, are still very relevant for those large applications, and there could be serious efficiency gains, but what we've really focused on is where those are not possible. So EMCP becomes critical when you think about electrification of platforms, elimination of hydraulics, electrification of aircraft in particular, because we're really focused in those cases on the weight, the efficiency, and the power consumption. So effectively what you have is no pitch control until you've got very, very large propellers or fans or turbines. So this was a study by a company called Wärtsilä. They're a global leader in energy and maritime solutions. So they introduced hydraulic pitch control to a ship's propeller. They achieved massive gains in efficiency, and when I say massive, it's 800 liters an hour in fuel saving for that particular vessel. With EMCP, eliminating the hydraulics, we can achieve way more than that, and we get other added benefits to the warfighter, as I mentioned, in terms of reduction in thermal and acoustic signatures. So this is Dr. McBain's invention. It's based around the concept of basically what is a reluctance motor. So the key to this technology is achieving that pitch control without hydraulics. So we leverage a reluctance motor arrangement combined with a ball screw, and that is mated to a nut that basically drives the linear actuation in a shaft. And we've done some pretty extensive electromagnetic studies. So effectively what we're doing there is causing a ball screw nut to move, and we've mated that to a Scotch yoke, and that linear actuation translates into rotational movement of the blades. For the next phase, we'll likely move to an axial reluctance motor design just to optimize space and performance for that. And part of this analysis we asked Kettering University to do for us. So we're still in the course of optimizing the motor design. We've optimized the mechanical design. This is completely scalable, up and down. Right now, the fan that we're building is 21-inch diameter, and it's going to move about 20,000 cubic feet per minute. Okay, so there is an embedded video in here, but I think we're having a little PowerPoint issues, but just to recap and compare, the existing mainstay solution for pitch control is to actuate it hydraulically via a piston. And we're going to achieve that through an electromagnet, and that is going to drive a ball and or lead screw, and it's basically a reluctance motor setup. It's pretty straightforward. I will note that we've got several patents for this technology that Dr. McBain has secured. We have done some pretty extensive market research. There is no setup like this on the market that we can find. Okay, so there is a video in there. I'm not gonna play it, and I'll keep this kind of short and sweet, but the link will be available to you guys. Okay, so we have also performed kinematic analysis, and we only need 17 watts of power to control the pitch. And that's, again, a fan that's generating 20,000 cubic feet per minute. And the power to actually drive the fan's probably 26 kilowatts, and we're using 17 watts of power to actuate the pitch of the fan. Okay, so currently how we're funding this effort, we have a Army Phase 1 SIBR. We're in the process of proposing a Phase 2, so we've been invited to do that proposal. The Phase 1 effort has really been focused on refining the mechanical and electromagnet design. We've engaged several Congress people and discussed this technology with them, so we have a couple of letters of support. We have letters of support from various thought leaders in academia and some other organizations who seem to be excited by the technology. So part of our next step in Phase 2, we're gonna look at a mixed flow fan arrangement. We're considering looking at a centrifugal arrangement. So right now it's a radial fan. We're thinking about applications where this could be successfully applied. So potentially the Stryker vehicle. So we've taken a look at that fan arrangement, and again we think there's huge efficiency gains to be done by implementing this technology. Jordan, did I miss anything? Good. Any questions, please?
Let's thank our speaker first.
Your design seems to have a lot of complexity. Can you share with us a little bit about your behavioral analysis?
Yes, maybe I could pass that to Jordan.
So on a typical hydraulic controllable pitch propeller, there's a large spring. There is actually a bearing from hydraulic controllable pitch. And for agricultural applications, it's only used there. If you look at the video later on, you can see its operation. It's extremely loud, so it won't be appropriate for silent watch. It's really only used for reverse the pitch so you can clean the filter. In the belly mode, then we eliminate that hydraulic string because we're using a jack like on an RV. You crank the jack on your RV, a human arm can spin it, and we have thousands of pounds of force pushing down on it, and of course it doesn't go anywhere, right? It's the jack. So having eliminated the string by using that jack, we simplify it, have very little significant.
Thank you.